let's work through some questions and the thought process that goes into the questions. That's more important. Okay, let's start with it. The questions that I'm doing right now are from chapter 9, end of the chapter pages. Let's do this one. I'm reading out the question. How close to the edge of a 20 kilogram table shown in figure can a 66 kilogram person sit without tipping it over? So I'm drawing the entire table right now. That's a table, and that's this stand. So the table is resting on two supports, and they've given some dimensions. Let me write all those dimensions. So this one here is 0.8 meters, and the width of the legs is 1.20 meters, and they gave you the entire length to be 2.20 meters, and they gave you this one as 0.5 meters. So you may use some of these dimensions as is needed. All right, before we go to that question, let's discuss something else right from here. And they also told you it's a 20 kilogram table. Always draw a big enough diagram so you can do a lot of stuff on the diagram, and your work will be more clear. Okay, so right now as it is, can anyone just tell me how much force does each support? How much force does each one take? Each of those legs, like this. Each of these legs, how much do they carry? How much? 98.1 newtons each. Right? Because 20 kilograms is the entire weight of the table. Like the top part. 20 kilograms times 9.81 is the weight of the table. And that is supported by two supports. So each support will take...
Are they both 0.5 meters from the end of the table?
Should be, yes.
Okay.
This is also 0.5 because this is 2.2 and that's 1.2, so it makes sense.
Yeah.
That should be. So this one is right in the middle, and therefore it's a uniform table. So 196.2 newtons is acting straight down here, and that is actually shared by these two supports, and so you understand that part too, right? Now the problem says there is a 66 kilogram person involved here. Suppose a 66 kilogram person stands right there in the middle of the table. If the 66 kilogram person stands right there in the middle of the table, like that. All right? So how much does each of these legs take?
Well, I'm sorry, how much? He's in the middle of the table.
He's right in the middle of the table stand, 66 kilograms. So if he's 66 kilograms and he's standing in the middle of the table like that, how much force will he be taking?
422, 421 for each leg.
How do you do it? How did you do it? What did you do?
Total mass.
Total mass, which is 20 times 66, which is 86, times 9.81, and then split it into two.
Wait, so plus or times 66?
Yeah, 20 plus 66, that's 86 times 9.81, gives you the entire weight, and these two are going to support exactly the same. Now watch. Suppose he's not going to stand in the middle. He's going to walk this way. Suppose he's going to stand here. Which leg will take more? The right one will be supporting more. Suppose he's standing right on this leg. Suppose he's standing right on here like this. How much does this leg take and how much does this leg take? If he's standing on the support, how much force is carried by this? How much force is carried by this? Go ahead. This is a 66 kilogram person standing right on this support. Will this carry something? So what will be the force here? What will be this force? And what will be this force?
Wouldn't it be 745?
Which ones?
The right one would be 745.
Looks like it. And that one? Are you
It would
thinking?
be 98. It would just be 98.
That will be 98.1. Because if he's standing on this, his weight is purely on this rest, right? But it was already having 98.1 earlier, so 98.1 plus his weight is going to be this one's share. And this one is going to be the same old 98.1. Is that clear? Now, but the question is not this at all.
Plus, wait, but you said it's going to be 98.1 plus 66? Or just
Times 9.81.
Oh.
66 times 9.81 is his weight, which is going to be added to the 98.1. So
That's
the
already,
force,
that's already coming from the table. So it's
the
table
table's
force plus
force
person
plus his weight. That's going to be here.
Okay.
And this one is just the table's contribution. Now,
Yes.
the question says, if he starts walking out, so the table is like projecting outwards, right? So if he starts walking outwards, how far can he go before it tips? Suppose he's going to stand somewhere else. Suppose he's going to stand somewhere else like that. How far can he go before it tips? Can he go to the tip here? Is it going to tip at some spot? It will apparently tip. And they're asking you to do this. Find how far it is. Find how far he can safely go and keep the table intact. So where is the tipping point? Now these are questions that you need to think practically too, and at the same time draw a diagram and place it properly. So maybe he won't be able to go here. So there is possibly a distance where he can potentially go. So let's call this x. Let's call that point x from this support. So this is your support F2. Now his weight is acting here. How much is his weight? 66 point times 20. 600
47. 647.46.
647.5 newtons. That is his weight pulling him from there. And he's at a distance of x, which we don't know, and that is what we have to find out. How far, where, till where can he actually move before it tips? So we're going to solve for that now. We're going to solve for x. Can anyone tell me how much is F1 at the point of tipping?
98.1.
Just as it was going to tip. 0. Because it's coming off. Like this. Right? These are the two supports. If he's going to stand here, he's just taking that off. At the point of tipping, it's not resting there at all, so there's only one support. Do you get it? So F1 will be 0 at the point of tipping. F1 will be 0 at the point of tipping, which means this part of the beam is not resting on the support at all. Ask me questions if you don't have priorities. So we confirm that yes, F1 should be 0 at the point of tipping, because at the point of tipping, 1 is coming off the support. So that means this support is not holding the table anymore. It's turning off. So that is 0. So how many forces are there? We have F2. And what do you think is F2 at that time? At the time when it is like coming off from the other stand, how much is F2?
Is it still 7.5?
plus 98.1.
Everything. Whatever this was not able to support anymore is going to be taken by this. So basically what you're going to say is the man and the whole 20 kilograms is going to be resting on this.
843.6.
That one. 843.6. That is going to be the entire force F2. We know it already, but that is not the question. The question is asking for this. So the best thing to do here is to take torque about F2. So F2 will be out of the picture. So take torque, net torque equals 0 about F2. Net torque should be 0 about F2. And how do you do it? Net torque is equal to 0 about F2. So what are the forces acting here? There is a force here which is 196.2 newtons, right? The weight of the beam. And there is the force over here by the person which is 647.5 newtons. Now we need to find out the torque about F2 by all the forces. There's not a single force here. F1 is 0. That's the first one. Which way is it going to turn the table? Which way is this force going to turn the table about this point? Counterclockwise. So positive. How much? 196.
Wait, which
Point.
game? Oh.
This one.
Oh, yeah.
This one is trying to turn it counterclockwise. So 196 and times perpendicular distance, which is 0.6. 0.6.
So it's in half of 120 or 1.2.
Yeah, exactly. This is so from here to here, how far it is exactly 0.6.
Is this at the tipping point, or we're not taking
At the
one
tipping
into
point.
calculation for zero?
This is at the tipping point. That's why we're taking this as
Okay.
0. Okay. And now, what is the torque offered by F2 about this point? 0. Now the last one is this, which is going to be, it's going to be clockwise, and which is going to be negative 647.5 times x. That's a perpendicular distance, equal to 0. Can you solve for x? Use your calculator, work it out. Solve for x. Yes.
0.182.
0.182 meters. I think the question is asking how close to the edge of a 20 kilogram, how close to the edge. So they're asking for this. So subtract 0.318. 0.318 meters. The question is asking how far from the edge of the table. So basically they're asking for this, but we solve for this, so it's okay. The whole thing is 0.5 meters. So once you discover this, you can actually find out this. So answer to the question actually, right? For convenience, we took this as our unknown, not x from here to here, because we want to make things easy. And once you discover x, then you go ahead and find out the other side of it. Any questions here?
Did you, sorry.
So distance from edge is equal to 0.318 meters.
And you added that to, or you subtracted that from 0.5.
Yeah. Subtract this from 0.5, which is from here to here, you get the other part. So look for the question. They are actually asking this distance, and that's it. So if they're asking for from the edge, then you go ahead. Or if they say from the middle of the table, then you go from there to there. So whatever they want you to find out, that is what. Suppose the person is already standing in the middle, and then say, how far from the middle of the table should he walk before it tips? Okay? So the problems as it is can appear complicated, but if you put all those variables and all that in the right place, and then put a little bit of that imagination, and then take a good pivot point, you will get it all right. But this one is the catch. Because you have to understand that at the point of tipping, this is coming off, which means there's no more force from the on the beam from here. So that sort of judgment should be part of your problem solving, and that comes only by almost thinking about it practically. Because normally what will happen is students will take this as an unknown, and then there are too many unknowns now, so you won't get a proper equation to solve it. Okay. Here is another problem. I'm showing the problem this time, I'm not reading it out. This meter stick weighs 100 grams. 100 grams. The meter stick weighs 100 grams. Sam, put that away. Close the book. Yeah. That's a meter stick which weighs 100 grams. I'm holding the meter stick like that. I'm holding it like this. I'm holding it at the 3 centimeter mark. Can you see the 3 centimeter mark? And the thumb is at the very tip. The thumb is at the very tip, and I'm holding it like this. The question is, find the forces offered by my forefinger and my thumb on the meter stick. What are the forces offered by my forefinger and the thumb on the meter stick? So before we go to the diagram, my forefinger, which is this, my pointing finger, this one, or index finger, that, which way is it pushing the meter stick? Up. Because sometimes students can actually make it, go down. And the way to understand it is upwards is what is my forefinger doing? If the forefinger was not touching it, it's going to fall this way. So the forefinger is actually pushing it up. And the thumb is pushing the meter stick down. So once you get that, go for the diagram. Once you get that, go for your diagram. So that's your diagram. That's the meter stick's 0 position, and this is the 100 position. And then the weight of the meter stick is going to act right in the middle, which is 50. And what's the weight? 100 grams, right? The weight is 100 grams times 9.81, which is 0.981 newtons. That's the weight of the meter stick. Now let's come to this edge. My thumb is pushing it down.
Why would it be point? Oh, yeah, you're right.
Okay? My thumb is pushing it down here. My forefinger is pushing it up at the 3 centimeter mark. Alright? So once you've drawn the diagram, you put everything that you know on the diagram, 0 centimeters, 3 centimeters, 50 centimeters, 100, and we have got this force. These are the two unknowns. Yeah.
What's that T?
For thumb. I put thumb and forefinger like that. Yeah. You can write F1, F2. It's purely.
So this from, there's two unknowns.
Yeah, these are two unknowns. So what do you do next? Now, is it in equilibrium? Is that an equilibrium, rotational equilibrium? Yes. So there are three forces acting on this. One is the weight, one is my forefinger pushing it, one is the thumb pushing it. In spite of the three forces trying to turn the object, it is not turning, which means it is in equilibrium. So we can apply the condition for torque straight away here. You don't need to do anything else. Where do you take the torque about? The thumb is better, fine. Take the pivot point as this. So net torque is equal to 0 about the thumb. Alright? So now start doing the torque. Thumb is right on the pivot. Therefore there's no torque. It's gone. This one, F. Is F turning the meter stick clockwise or counterclockwise?
Counterclockwise.
Counterclockwise.
Yeah.
Like if you just think of this force turning like this, you can see. That's fine. It'll take some time to really get that picture of which way it's going to rotate because it's not rotating. You're only like imagining which way it could. So this one is trying to turn it counterclockwise, so it is positive. F times, what's the perpendicular distance? 3 centimeters.
Oh yeah.
Then you can leave it in centimeters.
We can leave it in centimeters.
Yeah, because the other one is also going to be measured in centimeters, so it's fine. In this particular problem, you can keep your grams as it is or centimeters as it is, and they will cancel off because you're equating it to 0. Okay. And then this one is applying a torque about this point. Is it going to turn it
Clockwise.
clockwise? So negative 0.981 times perpendicular distance. How far is this force from here? 50. Equal to 0. Solve for F. Go ahead and solve for F.
Wait, where'd you get the 0.1 from? And
0.1 is the mass in 100 grams. It's 100 grams.
16.
I'm doing it.
Yeah.
I'm doing it properly in kilograms because I want to get my answers in newtons.
16.35.
So you get 16.35 or 4 newtons. If that is 16.4 newtons, how to find the other one? You can use the net x force equal to 0. No, net y force is equal to 0. According to net y forces, this is minus t, and that's plus f, and that is minus 0.981 equal to 0. That is your y condition, right? So what you see from here is f minus t is equal to 0.981. Since you already solved f, put it there. So 16.4 minus t is equal to 0.981. So t is equal to
15.4, yeah.
15.4 newtons. So you can see which one takes the extra load is the forefinger. The forefinger actually supports it more than the thumb. This one takes more. This one is fractionally less. Any questions on this? Yes.
So we didn't have to switch it to kilograms?
No, we did.
Oh, I did.
100 grams became 0.92. Otherwise you won't get Newton as your answer. See, we're getting Newton as the answer here because we switched it here. Centimeters, meters is centimeters is fine because if I change this to 0.03 and this to 0.5, it won't make a difference to your solution. Because if you divide this by 100 and make it meters, if you divide this with 100 and make it meters, since it's equal to 0, if you multiply by 100, everything is gone. So keeping in centimeters is fine.
So why isn't 15.4 negative?
Why is it negative?
Why isn't it negative?
Oh, we already marked it downward, so we are getting the magnitude.
Oh, okay, so you don't need to.
We are getting the magnitude of this force.
You can just, so you don't have to worry about it. It's also just not going to be negative if you keep it in the first equation that you have.
No, he's saying since
No,
it's
it's just
pointing
not-
downward,
Oh, okay.
why is it not coming negative? Because we already used assigned the signs. That's why it's not coming negative. But again, we have to assign the directions, otherwise we won't be able to apply the torque conditions properly. Like clockwise and counterclockwise, everything gets messed up.
So the force X versus torque. How is that in the middle? Like,
Say it again. Say it again.
So like, there's no forces going.
Oh, there's no forces horizontally at all.
There's only vertical. And so torque is just the weight, like each. Is it the same as? It's like, is torque the same as Fy in this case, but you're just picking up the weight?
No, torque is entirely different because when you take torque about a point, we are only looking for the turning effects.
Okay.
Like force times perpendicular distance, force times perpendicular distance. Whereas when you do the net y forces, you're only summing it
you're
up.
looking at the forces.
Only forces, yes. Got it?
I didn't even see that.
Next one. A traffic light hangs from a pole as shown in figure. So I'll draw the figure. A traffic light hangs from a pole as shown in figure. Again, draw a big enough diagram. If I'm using the entire board for the diagram, you better use it too, because then you can actually write stuff inside. Okay? So a traffic light hangs from a pole. Okay, that's the diagram. So that's a pole. And okay, now let me read more instructions here. The uniform aluminum pole AB is 7.5 meters long. The uniform aluminum pole AB is 7.5 meters long.
I can't like see what you're.
AB.
So for me,
The uniform aluminum pole AB is 7.5 meters long and has a mass of 12 kilograms. So this whole thing has a mass of 12 kilograms. The mass of the traffic light is 21.5 kilograms. Determine A, the tension in the horizontal massless cable, CD. They're calling it massless horizontal cable. And because it's horizontal, I put a 90-degree here, right? So cables that are used for cranes and all that, they are pretty light compared to what it is doing. So the mass of the cable itself is not significantly important, but it is pretty strong because they use kind of stranded steel wires to make it. And so they are pretty strong, they can actually flex, and they're not too heavy compared to what it is doing, right? Now, of course, they have to choose the proper material and stuff that can withstand. So they're asking you to find the tension here. So when you do this as a model and then figure out the tension, then you can figure out whether a cable has the required tension to do that job or not. You can't just put anything you want over there. If you put any cable over there, what if there's an extra wind and there will be tension, the tension can overshoot and then break the whole thing off. So you always look for strength of materials always for doing anything. For any construction, they always look for strength of materials. Can these bricks support the entire structure above that collectively? Because we need to know the compressive strength of the brick itself per feet or per yard, per meter. We need to know how much compressive stress can it hold. Anyway, the problem says this: find the tension here. That's the first question. So to find the tension over there. Now it's better to do the entire problem together. All right? What's the next objective? The next one says the vertical and horizontal components of the force exerted by the pivot A on the aluminum pole here. So they're basically asking you to find tension here and the horizontal and vertical forces right here, the components. That's it. So that's the entire problem. How do you start a problem? Draw a diagram. Use the data from the problem and then write all the data as much as possible right there. So you don't have to go back to the problem anymore. And then choose the appropriate equations.
What is that? Is that a D at the bottom?
This one?
Down.
It's done by the A.
This is
By
a.
the- what
Oh
was
no,
that
this is a
thing?
this is a hinge.
That, okay.
What do you do after the drawing and all that? The next thing is? Say it again.
Choose appropriate equations.
Label forces.
Label all the forces, wherever the forces are. Label all the forces. Now let's find out this. This cable that is sitting here, what is it doing to this aluminum pole? What if this is missing? What will happen to the aluminum
It's
pole?
gonna fall.
It's
So what is this doing?
Hold it up.
So you put the arrow this way. Into it.
What?
You said into it.
Hold it up.
Dude.
So you understand the importance of that cable on this at the point D. So that is. Now, what other forces are there? There's a force here.
Gravity.
How much is the weight of this?
2.5 times 921.
Do that. Tell me the answers.
210.9.
So 211 newtons. 211 newtons. That is the force. So when you know certain forces, just calculate and put it there. You don't want to put it in variables because when you know W, put those numbers. Read. So we have cleared this. We have cleared this one. As we come down here, what else?
Center of gravity.
This middle of this.
118 meters.
There is a force here, which is 12 times 9.81, which is
118.
118 newtons. 12 times 9.8, 118 newtons. And then if you go down to the hinge is offering two forces, a horizontal component and a vertical component. So we need to know which way it is going to be. So if I remove this pin, which way do you think this goes?
Down. Yeah.
Downward?
It's going.
So it applies on the
Like it is resting like this. If I remove the pin, what's going to happen is going to swing down here. So what is the pin doing?
Holding it up.
Holding it. Swinging is, yeah, holding it up. If I remove this entire section, the entire hinge from here, and give it a horizontal freedom, so it's resting like this. It's resting like this. If I remove this completely, which way do you think it's going to move?
What are you removing?
I'm removing this whole section. Imagine this hinge is not there. Nothing is there to hold it horizontally. So which way do you think it's going to go? It's going to go in, right?
Yeah. If you have what?
Like this.
Tension and strength.
If you remove the little thing, how's it gonna go
Look
out?
here. Like this. If I remove this board, which way do you think it's going to go?
Outward, like away from the.
So it's going to go like this.
No, like the bottom's
I'm-
gonna go outward.
I'm holding it from here.
The
Like
bottom's
this.
gonna go outward.
If I
Yep.
See?
Oh.
Like if I move my finger, it's gonna go. That's all.
What's this end? Watch this end. If this is gone, it's going in.
Oh, I see what you're saying.
Okay. So it's going to dig in. So what is this hinge doing horizontally? Holding it this way. Now if any one of this is wrong, the final answer will correct you and say, no, it's not that way, it's the other way.
Wait, what do you mean? So then it'll come out negative? Or?
Yeah, it will come out negative.
So
And then if it is only one unknown that is coming out negative, others are all good, then you can just flip the answer to positive and that's your answer. But if you make mistakes in this one's direction that way and this one's direction, everything is kind of changed, then the whole problem is messed up. So you can't make mistakes everywhere. One mistake is tolerable because when you do the problem, your answer will tell you that it is a wrong direction that you chose. All right. Conditions must be applied one by one carefully. Let's start with net X force equal to 0. Let's apply that. Starting from one end, scan it and do it. X forces only.
H.
Positive, negative. Positive. So positive H. Keep going. This is only vertical.
Tension.
Negative.
Negative tension. And then that's it. Equal to 0. So this only tells you that tension is equal to H. But we cannot solve for them both right now. What is your next thing? Net force in the y direction is 0. Net force in the y direction is 0. So start again this side. What is this? Positive V. Keep going. Negative 118. Keep going. That's horizontal. And then this one. Negative 211 equal to 0.
I thought in the clockwise direction.
No, we don't think of clockwise and all that here. When you're doing fx and fy, don't think about rotation.
Okay.
Just, is it upward, downward, forward, backward. So v is upward, this is downward, that's it. No more thinking about rotations. So what is v equal to? 329 newtons. So we solved for v already now. We solved for this, but we still have to solve for these two. So if one of them is solved, then everything's over.
So, why do you not have to pay attention to the clockwise, counterclockwise?
No, when you're doing the forces, we are not talking about rotation at all.
It's not torque.
When you do the forces, turning effect comes only for the torque. So, like if I'm holding this meter stick, the total force upward, this one pulling it up, this one pulling it up, and this one pulling it down, the weight, they should be balanced. Since it is not moving upward or downward, net force must be 0. And if I'm moving it like this, at a constant velocity or like that, so that's again the same thing, net X force is 0. If this meter stick is accelerating like this, the net force is not 0. There is a net force in that direction. That's what causes it to accelerate. Alright, so understood these two? Now let's apply the torque condition carefully. So the net torque is equal to 0. About which point do you want to take the torque? At A. So you say about A. Because V and H can both vanish from your equations. So we can get rid of both of them from our equations. And then you have a bunch of numbers and T, which is the unknown. If you take torque about A, these two are gone from the equation. Okay, so torque about A. Starting from the left hand side, V is not going to turn it, H is not going to turn it because there's no perpendicular distance. Keep going. That is going to turn this pole which way? Clockwise. So it's negative. We start with negative 118 times perpendicular distance. How much?
So it's half of 7.
Oh, yeah.
7.5 is that way. This is 3.75. Is that the perpendicular distance?
No, it's because it's the shortest point from the action. Right?
What did I say perpendicular distance is?
Shortest point
From the line of action of the force. That's the line of action of the force. Okay. We're looking for a perpendicular distance, so no comments anymore. We're looking for what's perpendicular distance? It's the shortest distance from the line of action of this force, and the pivot, which is basically this. We are looking for this distance. We don't want 3.75, we want this. And to find this, we have some clues for the angles. Right there is 37 degrees. If that is 37, that is 37 too, right? That is 37, that is 37. So once you know this is 37, and this hypotenuse 3.75, the adjacent side can be found out by 3.75 cosine.
3.7.
How much is 3.75 cosine 37?
It's about 3. Unless that's
No exact numbers. We need that.
2.99.
Make sure your calculator's in the degree mode. These are all mistakes that can go on.
2.87.
Is it degree mode?
Check.
2.99.
2.99?
Yes. 2.994.
I don't know, I'm taking your words. So check your calculator, if it's
Yeah,
degree
2.9.
mode. It is fine. All right. Now we are done with this force. Now we have to keep searching. Our next force is this, T. So T is going to turn this object in which direction?
Counterclockwise.
So it is positive. Positive T times perpendicular distance, which is
3.8.
3.8, straight away. Because this is the line of action of T, and that's a pivot, and they already gave you 3.80 straight away. There'll be some clue to get your distance.
So I'm basing it off T.
Huh? So T times 3.80. Now we are not done with that. We have to do the last one, which is this. And that is going to turn it which way?
Down. Clockwise.
Clockwise. So it is negative 211 times
7.5.
the shortest distance.
Wouldn't that be 2.99?
5.99.
So that is the line of action. And the shortest distance from here to there is this distance,
Isn't it 5.9?
which is going to be 7.5 cosine 37. 7.5 cosine 37.
It's 5.99.
5.99. Equal to 0. Solve for T. Go ahead. Solve for T.
Mr. Sam.
I got a very
What
large
about-
number.
Large.
Negative 480.5. What I do? Oh, I put 188 instead of 118.
Oh.
Mr. Sam.
Yeah.
What about the center of gravity though? Do you not have to use that?
We did this.
Oh, okay. Right.
This one.
That's one.
Yeah, negative 425.
Tension is
425.45.
so we got tension as 425, and therefore now since tension and horizontal force are exactly the same, we solve for that as well. So this force here, which the wall is applying horizontally, and this tension are both the same.
Wait.
As well. So we solve for three unknowns. V 329, T and H are 425 each.
How are they 425?
This is minus, and this also multiply this too. These are minuses, so it's like 3 and 6, 9, 9. Okay.
Okay.
You can see, as you can see, a good diagram will get you, will show you clearly the perpendicular distance and all that. If it is a very shabby diagram, you will be lost while trying to do the perpendicular distance. Because you cannot do much imagination on a shabby diagram. So diagram is an important thing when you're solving this. Half the problem is solved only made in the diagram. When you write all the data down, you're literally solving a lot of things right there. Another question.
Can we do a homework one? Or are we gonna keep
If you have difficulties, bring it up. If you have a difficulty, then bring it up. Now this is a wheel. This one is a wheel. Just like that. And the wheel has a mass of, let's say, 20 kilograms. And it has a radius of 40 centimeters. The wheel has a mass of 20 kilograms and a radius of 40 centimeters. So the wheel is placed against a step. It's like this. The wheel is placed against that step. You see that? And now we are going to apply a force here, like this. We want to pull it, pull it, pull it. How much is the minimum force that you need to apply in order to just make it climb up? That's the question. What's the minimum force that you need to apply in order to make it just climb up? So we are going to apply the force here, horizontally. What is that minimum force that is required to be applied horizontally in order to make the wheel climb? And the step is 25 centimeters. So now this is a situation where you're trying to solve for something which is obviously there. There is a force required, a minimum force required, and once it starts climbing, then that force can be dropped. It is only the initial rolling that requires that force. Right? If you need a 100 Newton force to just make it climb, as it starts climbing, you can reduce the force, and once it is over, then you're done. So the force that is required to be applied starts off from a certain value and a horizontal force. All right, now how do you go about doing this? Let's find out how many forces are acting.
One down.
One down. Okay. What is that? How much is it? So if you know the values, then start working on it.
196.2.
190.
6.2.
Right. 196.2 that way. What else?
Kind of move it so that the force acting on. Friction.
Is there force here?
Yeah.
Yeah. And that is 196.2 before you started pulling it. Before you started pulling it,
That's the end of the class. That's the end of the class.
this is the end of the class?
Yeah. Actually, a short class.
Okay, I'll finish off right now. Then I'll do it. This is easy. So when you start pulling from here, what's going to happen is this wheel is going to slowly lift off, right?
Yeah.
So when it starts lifting off, what will happen to this?
0.
0. So this will turn out 0 as soon as it starts moving. Now you're going to apply the torque. The best place to apply torque is here because there is a force acting here which we don't want to bring in. So when you take the torque about here, net torque equal to 0, watch what happens. This is a force. What's the shortest distance? Is it going to turn it clockwise or counterclockwise? Counterclockwise. So it's positive 196.2 times, what's the perpendicular distance? Is it the radius? That's a force. That is what the perpendicular distance is. Is that radius?
No.
That's not the radius. So to find this, we have to do a couple of things. Now this is 40 centimeters. And how much is this? So how much is this? 25. So how much is this?
15.
If you know 15 and 40, can you find this?
Yeah.
That is one thing. So I think it's like 37 something.
Why is it 15?
Because from here to here is 40.
Oh, yeah.
And from here to here is 15. So you got, and so that is 37. Next force is this, F, which is doing clockwise. So minus F times
37.
What is the perpendicular distance for that? From here to here.
15.
15 equal to 0, and then that will get you this. Should be around 300 or 400 or something, or 300 something.
Divided by 15.
400,
483.6.
483.
Yeah.
That's it. All right.